Hi everyone. So I already showed a method or an example. Well, it is the same example, but I showed a way or I solved it using, some algebra. Not that much, but some algebra. And I know there's a very few of you that, I'm not crazy about algebra, which is fine, I guess. So here's an easier way, and by easier, I mean with a little bit less algebra way to solve this one. I'm going to read it again. It says, a thin uniform cylindrical turntable of radius 2.9 meters and mass 17 kilograms rotates in a horizontal plane with an initial angular speed of 11 radians per second. The turntable bearing is frictionless. A clump of clay of mass 4 kilograms is dropped onto the turntable and sticks at a point of 0.91 meters from the point of rotation. That would be the center. Treat the clay as a point mass. Find the angular speed of the clay and turntable. Round to the nearest hundred. Okay, just like I said on the other video, I'm going to add a number so when I write my subscripts, I know what I'm talking about. For instance, the turntable, which is kind of like a cylinder, right? And sorry about that. I'm getting dizzy. There you go. A cylinder is also a disc, right? We'll use number 1 for that one. Now for the clay, we're told treat it as a point mass. So point mass, and that one will be number 2. Okay, let's write down what we have. Let's start with the given. Again, this is about angular momentum. Conservation of angular momentum. Given. So we are told that the system is made of the turntable and the clay. Okay, so I have the radius, so R1, that is the radius of the cylinder. That'll be 2.9 meters. And its mass, so mass 1, is 17 kilograms. Next, we know that the angular speed is omega initial, which is 11 radians per second. Now this is the angular speed of the system, right? Because afterwards, the clay sticks onto the turntable. Okay. Now we have a mass for the clay, that is M2, of 4 kilograms. And then a radius, so R2, of 0.91 meters, because that is the distance from the center. And we have to find omega final. This is about conservation of angular momentum. So don't forget the letter or the symbol for angular momentum is L, and it's simply I omega, where I is moment of inertia and omega is angular speed. Okay, so we have that the angular momentum of the system initially will be the same afterwards, right? Angular momentum of the system initial will be the same as angular momentum of the system final. Now we can see what are the parts of the system. And before, the only thing that is rotating is the cylinder. So then, let's define this moment of inertia. So let's start with L1, that is the moment of inertia of the cylinder, would be, the angular momentum 1 equals moment of inertia 1 times omega, right? Whether it's initial or final. Likewise, angular momentum 2 is the angular momentum of the point mass, so that would be moment of inertia 2 times omega. Well, for moment of inertia 1, we're working with a cylinder, and from the formula sheet you can see that the moment of inertia of a cylinder or disk is 1/2 mr squared. In this case, would be 1/2 m1 r1 squared because we're working with the cylinder. So this one will read angular momentum 1 is moment of inertia 1, that is 1/2 m1 r1 squared times omega. Now I want to focus on the moment of inertia. You'll see why, okay? And then L2 will be m2 r2 squared times omega. This is general, okay? Now I'm going to focus on the moment of inertia for each. So moment of inertia for the cylinder is this part without omega, 1/2 m1 r1 squared. The reason why I want to focus on it is I know the radius of the cylinder is not changing, nor is the radius of the, or better said, the distance from which the clay is positioned, right? The clay is not moving towards the center, away from the center. It doesn't say that. Nor do we have anything which suggests that the turntable is changing in size. That would be kind of weird, okay? So I can get a number for this. Let's do the same thing with moment of inertia 2, right? Because both moments of inertia will be the same before and after because we're not changing mass nor radius, okay? So m2 r2 squared. So now let's do this. Let's get the moment of inertia. I1 would be 1/2 mass 1, which is 17 kilograms, times radius 1, which is 2.9 meters. Don't forget to square that one. And then moment of inertia 2 would be no 1/2, just, oh, sorry. Oops, it was in 1/2. It's just like that because it's a point mass. So mass 2, that is 4 kilograms times 0.91 meters squared. Okay, I'm going to go back to decimals. I forgot to erase the answer, so you'll see it, but that's okay. We already know what we have to find, right? So that's going to be our answer. You'll see. This is the one with more algebra. So to find the moment of inertia of the first one is 1/2, 1/2, times the mass, that is 17 kilograms, times, what are you doing? There you go. 2.9, don't forget to square that one. And that would be the moment of inertia of the cylinder or disc. Now let's get the moment of inertia of the point mass or clay. That'll be 4 kilograms times 0.91. Don't forget to square it. And there you go. Those two. Okay? 17.485 and 3.3124. Let's hope I can memorize that. And I have 71.485 kilograms times meters squared. I know these are born units. And then we had 3.3214 kilogram times meter squared. You'll see why this is very, very helpful, okay? I'm going very slow, but the algebra will get easier. Now, back to the conservation of angular momentum, okay? So the system initially is only the turntable, that is a cylinder, so we'll have moment of inertia of the cylinder times initial velocity, angular velocity, that's it, right? That is the angular momentum, will be equal to moment of inertia of the cylinder times omega final plus moment of inertia of the clay times omega final, right? Because this is angular momentum, angular momentum, angular momentum. I have to solve for angular velocity final, so I have to factor omega final. So I1 omega initial, so I factor out omega final. That'll be I1 plus I2 Again, this is very good, or what's the word I'm looking for? I don't know. It's very cool, I guess, that we have a moment of inertia, or different moments of inertia which are not changing throughout the problem. And then to solve for it, we just divide by the sum of both moments of inertia, right? This cancels. Whatever we do to one side, we do to the other. And then omega final equals moment of inertia 1 times initial angular speed divided by moment of inertia 1 plus moment of inertia 2. You'll see how simple this would be when we substitute. We'll have final angular speed would be I1, which is this one, 71.485 kilogram. Let's get some more space. Times meter squared. Oh, I don't know what happened, guys. Meter squared times the initial angular speed, that was 11 radians per second. Man, I'm on the very, very edge of my writing tablet. That's why it's doing these crazy things. Sorry. There you go. That was bad. Let's try that again. I guess. And now we have I1, which is 71.485 kilograms times meter squared plus moment of inertia 2, which is 3.3124 kilograms times meter, sorry, not meter per second, meter squared. Okay, we go to decimals, and then it was 71.485 times 11 divided by 71 point, oh sorry, I put 5, huh? So it's 485 plus 3.3124, and there you go. As I said, we got the same number. And this one looks simpler than this, I think, right? 10.51. I'll use red, right? So it's 10s out. Final angular velocity equals 10.51 radians per second. And that is it. So for this one, the difference from the other one, the other video recorded, is I found the moment of inertia because it's not changing. My radius is not changing, nor is my mass. If you get that type of situation where the mass remains constant and both radii remain constant before and after, I think this is a good way to do it, right? I think it's a little bit faster. Or if you want to have fun, do the algebra. That's it.